Good morning, dear students. Welcome to our 5th online session for abstract algebra. Can you hear me? Okay, so last meeting, we discussed about binary operations and some mathematical systems and the operations defined on those mathematical systems. So if we look back, we started by defining a binary operation, okay, as a function or a mapping from S to S such that two conditions must be satisfied. First, it has to be well-defined and unique. And number two, the set is closed with respect to the operation defined or to that operation. And we looked into the set of the integers modulo m, and we have discussed the two operations on your set of integers modulo m, addition modulo m, and multiplication modulo m, and we were able to verify that these operations are binary operations on that set. Aside from your integers modulo m, we also look into the set of permutations on n symbols. Okay? The operation is multiplication. And then we were able to show also that the operation on the set S sub n is a binary operation. So for this morning, we will continue with your set of 2 by 2 matrices. Okay, so let's review your set of 2 by 2 matrices and the operations defined on your set of 2 by 2 matrices. So, a 2 by 2 matrix denoted as 2 by 2 and 2 by 2. Okay, why do we say 2 by 2 and we write it as 2 by 2? It's an array of 4 elements represented by this notation. Okay, A, B, the first row entries, and C, D are the second row entries. So, how many rows do we have? 2 rows. The first row has the elements A, B, and the second row has the elements C, D. And how many columns are there? We have 2 columns. A, C, okay, the entries along the first column, and B, D are the entries along the second column. Okay, so 2 rows and 2 columns. That makes 2 by 2. And that's what we call order or size of the matrix. Okay, so 2 by 2 or in general M by N. Okay, M by N. The sizes of a matrix is M by N, where M refers to the number of, what is M? M for rows, and N is for columns. Okay? Number of rows times number of columns. That gives the size or the order of a matrix. But we will focus our attention to set of 2 by 2 matrices only for this morning. And this is a special type of matrix because the number of rows equals the number of columns. So we call it a square matrix. So your 2 by 2 matrices fall under the classification square. Okay, it's a square matrix. A 2 by 2 matrix is a square matrix. So, 2 operations are defined on your set of matrices, addition and multiplication. So, in this notation, A and B are the first rows, C and D are the second rows. A and C are the first column and B and D your second column. So it says here, in general, an M by N matrix is an array of elements having M rows and N columns. Okay? So this gives the size or order of a matrix. Now, let's review the operations on matrices. Now, prior to that, now some relationship between matrices. When are two matrices equal? Okay, 2 by 2 matrices A and B are equal if and only if, okay, each of the elements in the first equals the corresponding element of the second. That is, if we have here, okay, the matrix A, B, C, D, it's equal to E, F, G, H only when corresponding entries or corresponding elements are equal. A is equal to E, B is equal to F, C should be equal to G, and D should be equal to H. So only when corresponding elements are equal, then the two matrices are equal. Now, let's move on to the operations on your set of matrices. So the first operation is addition. Okay? How do we add matrices? How are matrices added? And can we add two matrices whose sizes are different? Whose orders are different? No. Okay? So the two matrices should be or should have the same sizes or same order. The sum of two matrices A and B is obtained by adding, okay? By adding the corresponding elements of A and B. Okay, for instance, okay, A, okay, let this be A, okay, A plus B. By definition of the operation addition of 2 by 2 matrices, correspondingly adding A and E, yan, we add A and E giving A plus E here. And then B plus F giving B plus F here. Okay, and then C plus G, so you'll have C plus G, and D plus H, D plus H. Okay, let's look into one example. For instance, let this be the first, okay, matrix. The elements are 2, 3, negative 2, 0, plus the second matrix whose elements are 3, negative 1, and 4, negative 2. Getting the sum, we have to add 2 with 3. Okay? Yan, 2 plus 3. And then 3 plus negative 1 or 3 minus 1. There we have it. And then negative 2 plus 4. There it is. And then 0 minus 2. There we have it. And simplifying it further, 2 plus 3 is 5. Okay? 3 minus 1 is 2. Negative 2 plus 4 is 2. And 0 minus 2 is negative 2. Okay? So that's how simple it is. Now, prior to or before we proceed to the next operation, so let me ask you, how shall we justify closure here? Okay, how shall we justify closure? Okay, first condition is satisfied. The operation is well defined. How do we add matrices? We add corresponding elements. Okay, but first of all, sizes must be equal. Now, how do we satisfy or how do we justify closure property? Closure property is justified because looking at the result, okay? Take note that we added 2 by 2 matrices. 2 by 2 matrices. And the result is also a 2 by 2 matrix. Therefore, it is closed. Okay? So the set of 2 by 2 matrices is closed with respect to addition. When you add any 2 by 2 matrices, we are sure that the result is also a 2 by 2 matrix. Okay? So, closure property is satisfied. Therefore, addition of 2 by 2 matrices is a binary operation. Okay, now we proceed to the next. Now we move on to the next operation defined on your set of 2 by 2 matrices. Multiplication. Okay? Multiplication of 2 by 2 matrices. Now, before we go into multiplying 2 by 2 matrices, let's look into scalar product first. How do we multiply, okay, a matrix by a constant? K times A. Where K here is a constant. K times A is simply multiplying every term or every element multiplying every element of the matrix by the constant K. So, if I multiply the matrix whose elements are A, B, C, D with the constant K, then the product, scalar product, is equal to KA times, or KA, KB, KC, and KD. Okay? Now, we move on to multiplying 2 by 2 matrices. Now, in addition, or addition with respect to the set of 2 by 2 matrices is simply adding corresponding entries. Is that the same with multiplication? Is it the same with multiplication? How do we multiply 2 by 2, or how do we multiply matrices? How are matrices multiplied? Okay, for instance, let A be the matrix A, B, C, D, and B be the matrix E, F, G, H. Okay, E, F, G, H. Rows by column. Correct. So, Catherine said rows by column. Okay. So, we have to consider the first row. Sorry. Na-erase ko naman. This is AC. We get the first row entries multiplied to the first column. Okay? Multiplied to the first column of the second matrix. So that A will be multiplied to E plus B times G. A times E plus B times G. Okay? A plus E times B plus G. And that's it. Okay? So, ito yon. AE plus BG. Next, first row multiplied to the second column. First row multiplied to the second column will be AF plus BH. AF plus BH. Okay, row by column. So, we're done with the first row. We proceed to the second row. Second row multiplied to the first column. That will give, okay, CE plus DG. Correct? There. CE plus DG. And then finally, second row multiplied to the second column, you'll have CF plus DH. Okay? So, CF plus DH. So, let's look into one example. Let A be the matrix 2, negative 3, negative 7, 1/2, and B be the matrix 0, 10. This is 10. Okay, this is 10. And 3/2, negative 7. Find the sum first. A plus B first. A plus B, we add corresponding elements. 2 plus 0, negative 3 plus 10. Okay? Next, negative 7 plus 3/2, negative 7 plus 3/2, and 1/2 rather, plus negative 7. There, 1/2 minus 7. And when simplified further, 2 plus 0 is 2. Negative 3 plus 10 is 7. Next, negative 7 plus 3/2 is negative 11 over 2. And then 1/2 minus 7 is negative 13/2. Now, how about A times B? Okay, A times B. Okay, first row multiplied to the first column. Okay, first row multiplied to the first column, so you'll get 2 times 0, okay, plus negative 3, 2 times 0 plus negative 3 times 3/2, correct. Next, first row, second column. Okay, 2 times 10, correct, plus negative 3 times negative 7. Okay, now we move on to the next. Second row, multiplied to the first column. Negative 7 times 0 and 1/2 times 3/2. Finally, okay, second row, second column will have negative 7 times 10 plus 1/2 times negative 7. Okay, which when simplified gives 2 times 0, 0 plus negative 3 times 3/2 is negative 9 over 2. Correct. Next, 2 times 10 is 20 plus negative 3 times negative 7 is positive 21. So you have 41. Then we have here, second row, negative 7 times 0, 0 plus 1/2 times 3/2 is 3/4, correct. Negative 7 times 10, 70, negative 70 minus 7/2 is negative 147 over 2. So this is the product of the matrices A and B. Okay. Now, let's look into the properties. So now that we have reviewed the operations on your 2x2 matrices, now we are ready to look into the properties. Now, this is to get ready also for the next topic, which is groups. Because for groups, we shall be verifying 4 properties, not only closure, but 3 other properties. Okay, so when is a mathematical system considered a group? That we will find out in the next slides. Okay, so what are the properties then of the operations with respect to, or in M rather? So 1, let's go back to the previous. When we multiply a 2x2 matrix with another 2x2 matrix, the result is also a 2x2 matrix. So that one satisfies the closure property. So looking at this, okay, let me highlight the properties with respect to the binary operations. In M, the set is closed with respect to addition and multiplication. Okay? When you operate on 2, when you add 2 2x2 matrices, when you multiply 2 2x2 matrices, the result is also a 2x2 matrix. Okay? Therefore, it is closed. Next, is addition commutative? Now we can verify. Okay, you can verify looking at this. If we check on B plus A, Okay, B plus A, will it give the same answer as this? Yes, because you'll have 0 plus 2 is 2. 10 minus 3, 7, just the same. Okay, 3 over 2 minus 7 is just negative 11 over 2. And negative 7 plus 1 half will still yield negative 13 over 2. Okay, so it's still commutative. B plus A is equal to A plus B. But the question is A times B equal to B times A? That's the question. Okay? Is A times B equal to B times A? Will it give the same answer? Now let's show a counter example. Let's copy. Our A in the previous is the matrix whose elements are no. Okay, you said no. Let's just show a counter example. 2, negative 3. Sige. Okay, 2, negative 3. Negative 7, 1 half. And B is 0, 10, 3 halves, negative 7. 0, 10, 3 halves, negative 7. Okay, let's take the product. A cross B. A times B, what will it be? Or B. No, we already have A times B. What are we going to show? Or what do we have to look into? Let's look into B times A and compare whether it will be equal to A times B. So B times A, we start from here. Okay? So first column or first row multiplied to the first column, what will that give us? 0 times 2. Ay, bakit yun? Okay, 0 times 2 plus 10 times negative 7, correct? And then 0 times negative 3 plus 10 times negative or 10 times, yan, wait, let me, yan. This with this, and then this with the second. Okay? So, 0 times negative 3, 10 times 1 half. 10 times 1 half. Looking at this alone, if you simplify the first, 0 times 2 is 0, and then 10 times negative 7 is negative. This will yield negative 70. Okay? This will give negative 70. Now, going back, look at this. The first entry for A times B is negative 9 over 2. Okay? Look, I want you to look into the first entry here. It's 9, negative 9 over 2. Whereas for B cross A, B times A, for B times A, the first entry along the first column or first row rather is negative 70. So we may not continue. Okay? So from here, you're right. It's not commutative. So please put that in mind. Okay? A times B is not equal to, okay, A times B is not equal to B times A. A times B not equal to, let's go back. So, what's your answer here? Is A times B equal to B times A? Answer is no. So, only addition is commutative but not multiplication. So, please put that in mind. Now, we move on to the next. So, we're done with the first property, second property. Next, number 3. Is addition and multiplication in M associative? Okay? Is addition and multiplication, or are the operations addition rather and multiplication in M associative? Now, let's again recall what associativity means. Associativity means grouping. It has to do with grouping, yes? Changing the grouping of number of the matrices to be added or to be multiplied does not affect the sum or the product. Okay, can you check on associativity whether it holds? Then, may we leave this? Let's leave this first. X muna natin. Groupings. How about this? Now, we move on to the fourth property. Is there an identity with respect to addition? Identity. Now, let's recall the definition of identity. So, when we speak of identity element, okay, identity element, that is that which when added to A, okay, results to A itself. Yes? With respect to addition. No, with respect to the operation addition. Okay? That which when, let me write it as I. Sige, I na lang. Let's use I for identity. Okay? A matrix plus its identity will give the matrix itself. So, if our matrix is A, B, C, D, plus, what should this be? So that the result is the previous matrix, A, B, C, D. What should this be? Excuse me for a... Okay, what should this be? You're right. All entries, a zero matrix. So, 0, 0, 0, 0, 0. So, A plus 0, A, B plus 0, B, C plus 0, C, and D plus 0. So, with respect to the operation addition, okay, for addition, the identity element I is the zero matrix. Yan. Yan. Okay? So, this is the identity element with respect to addition. Now, how about for multiplication? What is I? Okay, that's the question. For multiplication, what is the identity matrix? So, again, by definition, A times I should be equal to A. Okay? Now, we're moving on to multiplication. Okay? So, your A is the matrix A, B, C, D. What should this be so that when I multiply it to A, B, C, D, the result will still be A, B, C, D. Okay? All ones? Okay, the identity matrix with 1. Are you sure it's all 1? It's a square matrix whose elements are 1. 1, all ones? 1, 1, 0. Okay, 1, 0, 0, 1. Take note that the main diagonal is a square matrix wherein the entries or elements along the main diagonal are 1s and the rest are 0. Okay? So it's a square matrix wherein the elements along the main diagonal are 1 and the rest are 0. Okay? The rest are 0. We can always verify because if you multiply the 2, you will have, if I multiply the 2, what will I get? A, this times this, you'll have A times 1, B times 0, that will give A, correct? And then AB times the next column, A times 0, 0, B times 1 will give B, correct? Next, CD or C times 1, that will be C and D times 0 is 0, so giving C, correct? And then CD times the second column, C times 0, 0, D times 1 will be D. Okay, therefore, going back, the identity matrix with respect to multiplication is a square matrix whose, or a 2 by 2 matrix whose the entries wherein the entries along the main diagonal are 1, 1, and the rest are non-zero. Okay? So, there exists, let's check this now. There exists an identity element in M with respect to addition. And this is the identity element with respect to addition. Okay? So this is I, identity element. There exists also an identity element M with respect to multiplication, and that is the matrix, and this is this matrix rather. Now we proceed to the inverse. So we're done with the identity. How about inverse? Are there questions here? None. We now move on to inverse. First, with respect to addition. Okay, with respect to addition. By inverse, we mean that element which when added to A gives the identity element. Okay? What should this be? May we have it, since we are talking of addition, then may we have it as negative A. So if my matrix is this, what should be added to that matrix in order to get the identity element with respect to addition? What did we say about identity element with respect to addition? This. Okay, this is the identity element with respect to addition. So, the result here should be 0, 0, 0, 0. Okay, what should this be? This should be, what should I add to A to get 0? The negative of A. What should I add to B to get 0? The negative of B. What should I add to C to get 0? The negative of C. And what should be added to, sorry, this should be D. This should be D. What must be added to D to get 0? It should be negative D. So therefore, okay, A inverse is simply the negative of every element. Negative A, negative C, negative D. And that's it for addition. Now, the next question is, what about for multiplication? What about for multiplication? Again, by definition, when we speak of inverse, once again, it's that element which when multiplied to a given matrix, may we denote it as A raised to negative 1, will give the identity element. Now, what is our identity element with respect to multiplication? What is our identity element with respect to multiplication a while ago? We said the identity element is this. Okay? The identity element with respect to multiplication is this matrix. Okay? A square matrix wherein the main diagonals are or have the elements 1 and the rest are non-zero. So, moving on. This should be, okay, A, B, C, D times, let's denote this as to be X, Y, Z, W should give a product of, what is our identity? 1, 1, 0, 0. Okay. This is what we are going to find. Okay, what is this? What will this be? What will this be? Although You have a ready formula for this, yes? Okay, looking at our PowerPoint presentation, ito. D over, yan, D over AD minus BC, negative B over AD minus BC, negative C over AD minus BC, A over AD minus BC. Let's show how this was derived. Okay? How was this derived? How was it derived? So that you don't have to memorize. Ano na nga pala yun? D ba? D ba o negative A or negative D? Is it D over AD minus BC or we swap? Which one are we going to swap? Which one are we going to get its negative? No, so that you don't have to memorize. So let's show how the formula or how these entries were obtained. Okay? So let's go back. Okay, from here, we can come up with a simultaneous or a set of simultaneous equations from here. So, if we multiply A, so let A inverse, this is what we are going to find, yes? A inverse be represented by X, Y, Z, and W. And we have to find the values of X, Z, W, and Y. Okay? From where? From here. Okay. So let's multiply. Let's multiply. So from the definition, first row, first column. First row by first column. So what will that be? AX plus BZ would be equal to this. Okay? Would be equal to 1. Correct? Would be equal to 1. So, AX plus BZ should be equal to 1. Next. Next, first row, second column. What will that give us? AY plus BW should be equal to 0. Okay? Should be equal to 0. So, equals 0. So, let this be equation number 1 and let this be equation number 2. Now, we proceed. Get the second row, multiply it to the first column, and that should be equal to this. Again, first or second row multiplied to the first column, that would be CX, okay, CX plus DZ is equal to 0. Again, okay, this multiplied to this should give this. Okay, so CX plus DZ should be equal to 0. And finally, second row, second column should be equal to this. Okay? So, it should be equal to 1. What will our equation be? CY plus DW is equal to 1. Okay? CY plus DW should be equal to 1. So, we were able to set up 3 equations or 4 equations. Equation number 1, equation 2, equation 3, and equation number 4. I will begin with equation number 1. From equation number 2, AY plus BW is equal to 0. Take note that these are what we are looking for, X, Y, Z, W. So here, I could express W in terms of Y, okay, as BW is equal to negative AY. And so, W will be equal to negative AY over B. Okay? So negative W, or negative, W is equal to negative AY over B. I will use this. Remember that I got this from equation number I got this from equation number 2. Once more, this is from equation number 2. Now, let's take any of the equations. AX, let me check once again. Our equations are correct. AX plus BZ equal to 1. AY plus BW equal to 0. CX plus DZ equal to 0. And CW plus DW equal to 1. I could use equation number 4. Okay? In which equation could you find W? Here. You could find W here in equation number 4. So, I could use equation number 4 in my next step. Put this, okay, we will put this in equation number 4. And equation number 4 from equation number 4. Let this be step number 1 and step number 2. Taking equation number 4, which is CY plus DW equal to 1, CY plus DW is equal to 1. And we found out that W is equal to this. Okay? So, I will have to write here now CY plus D times W, which is negative AY over B is equal to 1. Okay? Now, take note that Y is now common to both. So, we can factor it out. So, this one becomes Y equal to, Y times rather. Okay, Y times, factor it out. Y times C minus AD all over B. Okay? C, factor, C, Y, bring this out, factor it out. There you have it. So, times C minus AD over B. Okay? Is equal to 1. I can express this into Y times, okay, BC minus AD all over B is equal to 1. Now, Y will be equal to, divide 1 by this, it's the same as 1 multiplied to the reciprocal, yes? So, it's like multiplying both sides by, in fact, multiply the whole equation rather by B over BC minus AD, correct? Okay, minus, AD. And that would cancel this out. So, Y will be B over, okay, BC minus AD. Okay, BC minus AD. But we could rewrite this as, negative B. I think the space will not be sufficient, so may we move to the next. Okay, so from here, from Y is equal to B over BC minus AD, we can rewrite this into Y is equal to B over the negative of AD minus BC. Okay? And further, we could write y as negative b all over AD minus BC. So now we have y. Okay, now we have y. And then, take any of the equations. So we found y. Going back. So looking back at this, w. Okay, looking back for w, we can now replace y with the expression that we obtained. So from here, so w, as we found out from the previous, is equal to negative ay over b. But we found out that w is equal to negative, let's go back, w is equal to this. Okay, w is equal to negative ay over b. But w is equal to negative ay over b. So, what will w be? Negative a over b times negative b all over AD minus BC. Okay? So that means we have replaced y with this. Okay, from here. And so, continuing further, simplifying it further, this with this will cancel out. B, okay, let's use another color. With this, will cancel out, leaving w equal to a over AD minus BC. So now we have w. We have x, we have y, w. What else are we going to find? X and y, and x and z. So we still have to look for x and z. Now going back, equation number 1 from equation number 2 rather, or from equation number, let's go back. Equation number 3. May we use equation number 3 now? Equation number 3 and equation number 1. Okay? Equation number 3 and equation number 1. Equation number 3 is this. Cx plus dz equal to 0. Let me copy. Equation number 3 is Cx plus dz is equal to 0. Then express z in terms of x, dz is equal to negative cx, and so z is equal to negative cx all over d. And then from equation number 1, we did not use equation number 1 yet, ax plus bz is equal to 1. We simply have to replace z with this now. Okay, so let's now replace z with what we obtained from the previous. So, ax plus b times, what did we get for z? Negative cx over d is equal to 1. Okay, now since x is common to both x, we can factor it out. So, factoring out x, we get x times a minus bc over d is equal to 1. Okay? Or x times AD minus BC all over D is equal to, all over D. All over D is equal to 1. Now, dividing both sides or multiplying both sides by D all over AD minus BC, what is x equal to? X equal to D over, this will cancel out now, okay? Over AD minus BC. So now we have X. Okay, so meron na tayong X. So finally, si Z from here. Okay, so from Z equal to negative CX over D, then Z will now be negative C over D times X from here times X, which is from our previous step, X is this. X will be, okay, D over AD minus BC. Okay, what will Z be from here? Z will be, D will cancel out. Canceling out D, what did we get? What do we get rather? D is now equal to C negative over AD minus BC. Okay, so that's it. We were able to get all the four. So, Y is this? Y is negative B over AD minus BC. W is AD over AD minus BC. X is D over AD minus BC. And Z is this. Therefore, our inverse matrix must be, okay, X first. What is X? Where is X? This is X. Okay, so D over AD minus BC, this is X. How about Y? What is our Y? Here is our Y. Okay, and our Y is negative B over AD minus BC. Okay, X, Y, Z. What is our Z? There. Okay, our Z is this. Okay, so negative C over AD minus BC. And our W, which is, this is our W, okay, is A all over AD minus BC. This is the inverse matrix. Okay, so that's how the inverse matrix was derived. Okay, so the inverse matrix is given by this. So take note that they have a common denominator. Yes, AD minus BC. And that in fact is your determinant. The determinant of the 2 by 2 matrix is AD minus BC. Yan. AD minus BC, AD minus BC, AD minus BC. What happened to A and D? Swap places. Okay, A and D swapped places. How about B and C? Same places, but we have to get their negatives. Okay, so going back, let's compare. Correct? Okay, compare it here. This is in fact what we have just derived. And this gives the inverse, okay, inverse of a 2 by 2 matrix. DA swap places, and then B and negative C retain their places but get their negatives. And then divide each entry by the determinant. Now, please take note that when BC, or should I say, when AD minus BC is 0, then the inverse does not exist. Okay? Inverse does not exist. Please take note of that. When the denominator, when the determinant, this is in fact, this is the determinant. This is in fact called your determinant. It's the determinant. Next question that we have to answer. Is multiplication left and right distributive over addition? Okay, I'll leave this as your assignment. Check on distributivity. Is multiplication left and right distributive over addition in the set of 2 by 2 matrices? Now we move on to the next. So, from your set of 2 by 2 matrices, I will introduce another system to you called the set of symmetries of a square, or motions on the plane. Set of motions on the plane. But before that, let's first define what a group is. Okay? So from binary operations, we're moving on to groups. What is a group? Okay, by definition, a group is a set G of elements. So we're talking of a set with elements together with a binary operation satisfying the following properties. Okay, so take note of the properties that must be met. The first property says that set G, the set, must be closed with respect to the operation. Okay? Next, that the operation is associative. Okay? Changing the grouping does not matter. Next, that there exists an identity element E. Hindi siya I. E ang ginamit. Okay. There exists an identity element in G for that operation. Fourth, there exists an inverse. Okay? An inverse in every element. Okay? Take note, every element. A in G, relative to the operation or with respect to that operation. So, a group is commutative if and only if the operation is commutative. So, this is a special type of group. There is what we call a commutative group. When is it a commutative group? When the operation is commutative. So, basically, there are how many? 4 properties that should be satisfied. So, if a mathematical system, meets all the 4, then it is considered a group. And further, if the operation is commutative, then it is a commutative group. Now, let's look into examples of groups. Okay, number 1. The first, the set of all integers, set of all real numbers, and the set of complex numbers form a group under the operation of addition. Okay, under the operation of addition. Why? So let's look into the properties one by one. What's the first property? Is it close with respect to the operation addition? Yes, when you add any two real numbers, the result is a real number because R is close with respect to ordinary addition. Okay? R, the set of real numbers, is close with respect to addition. When we add any two real numbers, the result is a real number. So, correct. Check. How about associativity? Oh, we have proven that in the past. Okay? And accepted. Okay? Changing the grouping of numbers to be added does not affect the sum. Next, there exists an identity element. Okay? For addition, yes, the element is 0. The identity element with respect to addition, take note, we are talking on addition. Talking about addition, I should say. Next, is there an inverse for every element? Yes. How do we get the inverse with respect to addition? Just the negative of the number. Okay? So, every element has inverse? Yes, even 0. 0 plus 0 is 0. 1 plus negative 1 is 0. Okay? So, correct. Therefore, number 1 here is the set of integers, all real numbers, and even your complex numbers, okay, form a group under the operation of addition. Next, number 2, set of permutations on n symbols. Recall from last meeting, set of permutations, your alpha, your beta, your rho, looking into the first property. So put this in mind, permutations on n symbols. So let's check on the properties. Number 1, is it closed with respect to the operation? I asked you before to complete the table. Are all entries of the table members of S sub 3? Okay, if you could recall, how many elements are there for S sub 3? For S sub 3, we had 6, yes? 3 times 2 times 1, so 6 possible arrangements. So your S sub 3 has 6, and your table is a 6 by 6 table, yes? 6 times 6, 36. So, in your table, all entries are elements of S sub n. Therefore, closure property is satisfied. So, let me check. Closed siya. Okay, closure property. Is it associative? That we did not check. Okay, that we did not check. On the closure property, associativity rather. Is it associative? Okay, let's look back. Nakalimutan nyo na. So let's look back. What was our let's say let's say alpha is 1 2 3 1 2 3, and then let's say beta is equal to 1 2 3 1 3 2, and let's say phi is equal to, let's say 1 2 3 1 2 1 3. Okay, let's just show associativity. By associativity, we mean beta times phi. Will this give the same answer as will this be equal? Okay, let's begin from here. That's just to show associativity. Ito, what will this be? What will this be? Let me copy. 1 2 3 1 2 3. Okay, and the result from here. Okay, so let's see. Begin from phi, yes? 1 is mapped to 2, but 1 is mapped to 2, but 2 is mapped to 3. So 1 3. Next, in phi, 2 is mapped to 1. Sorry. Two is mapped to 1, but 1 is mapped to 1. So, 2, 1. Next, phi maps 3 to 3. 3 is mapped to 3. 3 is mapped to 3. Wala na tuloy ako. 3 mapped to 3 and 3 mapped to 2. So, 3, 2. Finally, what will this be? 1, 2, 3. 1 mapped to 3. 1 is mapped to 3, but 3 is mapped to 3. 2 is mapped to 1, but 1 is mapped to 1. 3 is mapped to 2. Okay. 3, 1, 2, which is in fact, what's the result? Let me compare it with this. What will this be? Alpha times beta, what is it equal to? Start from beta. Beta maps 1 to 1, 1 to 1, and then 1 to 1. So 1, 1. 1, 1. Next, 2. Beta maps 2 to 3. Beta maps 2 to 3. And 3 is mapped to 3. So 2, 3. Finally, beta maps 3 to 2. Okay, 3, 2. Times phi, which is 1, 2, 3. 2, 1, 3. What will this be? Start from here. 1 map to 2. 2 map to 3. Okay, next. 2. 2 map to 1. 1 map to 1. And then finally, 3 map to 3. 3 map to 2. Are they equal? Obviously, they are equal. So, see? Okay? Yan. They are equal. So, this one satisfies your associativity. Associative property. So, your S sub n with respect to that operation, multiplication, is associative. Okay? Associativity or associative, rather the operation, not the set. Sorry. The operation is associative. Okay? Multiplication of permutation of n symbols is associative. So, let's go back to that question then. Going back. So, correct. It's associative. Now, is there an identity element? Identity element, we found out that there is an identity element before, and that is alpha. Okay? Yung una. Yung 1, 2, 3, 1, 2, 3. Next, is there an inverse? I think we ended up with this also. I asked you before to look for inverses. Do all elements have inverses? Okay, do all elements have inverses in your S sub n? I gave that as an assignment. All elements have inverses? Yes? Yes. Therefore, your S sub n, set of permutations of n symbols with respect to the operation defined on it, is a group. It's a group. Okay? Now, we move on to the next. So, we're done with number 1. Number 2, how about this? Z sub m. Okay? With respect to the operation addition modulo m. Okay? With respect to Z sub, with respect to addition modulo m. So, Z sub m with respect to the operation addition modulo m. Number 1, is it closed with respect to, is the set closed with respect to the operation? Yes. Okay? Yes. You can check your Cayley table. All entries are members of Z sub m. Number 2, what's the second property that must be satisfied for a group? Okay, the second property is associative property. Is addition modulo m associative? Yes, you can verify with few cases. For example, let's say in Z sub 8. Okay, example, in Z sub 8, 3 plus 5 modulo 8 plus 6. Okay, is it equal to the quantity 3 plus 5? Are they equal? Let's verify. So first, 3 plus 5 modulo 8 is 0. Correct? Ito. 3 plus 5 modulo 8 is 0. Okay, plus 6 modulo 8. Will this be equal to this? 3 plus, okay, next, 5 plus 6 modulo 8. 5 plus 6 is 11. Modulo 8 is 3. Yes? Is equal to 3. So getting the sum of the left hand, that's 6. Is it equal to this? Obviously, they are equal. Okay, so associativity is satisfied. Or, okay, that's it. Now we proceed to the third property that must be met. There exists an identity element in G for the operation. Take note that we are talking about addition. Number 3, there exists an E, identity element. Yes, and that identity element is in fact is 0. Because adding 0 to any number will result to the given number. And then fourth, last property that must be met. Ayan. Is there an inverse for every element? Okay. Inverse. There exists an inverse. Okay. For every element in Z sub m. Yes, and the inverse is negative of A. Negative of A. Negative of A, I'm not referring to the negative of A because remember when we speak about Z sub m, these are all positive. Okay? These are all positive divisors of m, or not divisors, remainders upon division by m. Take note that your Z sub m has the elements 0, 1, 2, 1, 2, 3, until m minus 1. Okay? Inverse of, let's say, Z sub 8. In Z sub 8. Inverse of 1, what is it equal to? What should I add to 1 to get 0? Remember that our identity element is 0. And when you speak about inverse, that element which when added to a given element will result to the identity, and we shall denote it as negative A. So please do not say positive 1. No, because this one only implies, we are using the symbol only to mean the inverse of negative 1 in Z sub 8. Okay, so for your Z sub 8, take note, once again, that your elements are, for Z sub 8, your elements are 0, 1, 2, 3, 4, 5, 6, and 7. Hanggang dyan lang. So if I say negative 1, what does it mean by this? The additive inverse, okay, of 1. What must be added to 1 to get 0? Edi 7. Okay. So, 7. What is the inverse of 2? Additive inverse of 2. What should I add to 2 to get 0? That would be 6. And so on and so forth. So, all elements have inverses. With respect to addition, yes. Negative 3. Additive inverse of 3 will be 5. Additive inverse of 4, 4. Additive inverse of 5 is 3. Additive inverse of 6 is 2. Additive inverse of 7 is 1. Additive inverse, please. Okay? You might say, what is mom doing? Negative 0. This is only to symbolize. Okay? Just to represent, okay, additive inverse of 0. Okay? But there is no such a thing as negative 0. Huh? Okay, this is only to mean the inverse, additive inverse of 0 is 0. So take note, all elements of Z sub 8 have inverses with respect to what operation? With respect to addition. Therefore, okay, closure property, check. Associative property, check. Existence of an identity element, check. Existence of inverses for every element, check. What can you say about Z sub m? Z sub m is a group under the operation addition. Okay, I hope that is clear now. Okay, now, additional property. Is it a commutative group? Is Z sub M a commutative group under addition? You know very well that addition of the set of real numbers is commutative. 2 plus 3, 3 plus 2 does not matter. So automatically we can say that Z sub M with respect to addition is a commutative group. Okay? So what shall we write here? Z sub M with respect to addition modulo M is a commutative group. It's a commutative group. Your assignment will be numbers 4 and 5. Numbers 4 and 5. Last for this morning. Kaya pa? Kaya nyo pa? Kasi ito bago. May bago tayong set. Have you encountered the set of symmetries of a square in the past? Set of symmetries of a square. A square. Kaya daw nila. Kakayanin nyo? Ito, may ganito kayo? Do you have your... Ay, not yet daw. Okay, so not yet. Oh, this is something new. Yeah, I hope you could follow. Okay? No. So the next mathematical system that we are to study, take note that for algebra, abstract algebra, we will be talking about more about properties and mathematical systems. You will encounter more unique mathematical systems as we go on with our study of groups, of rings, of subgroups, cyclic groups, and so on. Okay, the next mathematical system that we are to study is the set of symmetries of a square. So, let the square be located in the coordinate plane so that the center of the square, panglas na, okay, the center of the square is along the point of origin. Okay, the center of the square is along the is at the point of origin, and the sides are parallel to the coordinate axis, parallel to the x-axis, parallel to the y-axis. Okay, so this figure has 4 lines of symmetry. The coordinate axis, x-axis, y-axis, diagonal 1, diagonal 2. So there are 4 lines of symmetry. So your first diagonal, let me just label. I'm going to label. We will call the diagonal from quadrant 1 to 3 as the first diagonal, and that diagonal from quadrant 2 to 4 will be your second diagonal, diagonal 2, diagonal 1, and diagonal 2. Now let's label R sub 0. There are 8 motions. There are 8 motions, and it will be represented by the following. R sub O, that's the original position. R sub 1 is counterclockwise rotation by 90 degrees. R sub 2 counterclockwise 180 degrees. And R sub 3 counterclockwise rotation by 270. Then aside from that, we also have translations or reflection. We reflect it with respect to the y-axis, that's flipping it over, okay, with respect to the y-axis, or to the x-axis rather, and then y is the reflection with respect to the y-axis. D1 will be reflection with respect to the diagonal 1, like this, and then D2 will be reflection with respect to the second diagonal. So that we will have uniform results, may we label R sub 0 as that square whose vertices are as follows. Yan. Okay? 2, 1. Yan. So, this is the original position. Original position. I want you to pay attention to the slide so that you will have a guide. Look at this part, RO. Get your square and label it in this manner. This is the original position. So that when I say RO, ito yan. Okay, ito yung RO nyo. And then what will be R2 or R1? R1 is counterclockwise rotation of 90 degrees. Okay, counterclockwise rotation of 90 degrees. Counterclockwise. This is clockwise motion. Okay? Clockwise. So, counterclockwise, it's the opposite. So, it would be like this. So, what will appear on the top vertices? Your top vertices will now be, instead of 2, 1, it will now be 1, 4, 2, 3. It will now be 1, 4, 2, 3. Can you see this? It will now be 1, 4, 2, 3. Again, because the original position was like this. Okay, the original position was this. RO. This is RO. And then R1 means counterclockwise rotation by 90. Isang ikot. 90 degrees. So, baligtad ako. So, siya. 90 degrees. So, ito. So, your vertices on the upper part will now be here, 1, 4, 1, 4, 2, 3. 1, 4, 2, 3. Okay? Next. So, from 1, 4, 2, 3, now we flip it again, or move it again by 90 degrees counterclockwise. So, your top vertices will now be, okay, yan. Top vertices will now be 4, 3, and then your vertices below will now be 1, 2. Can you follow? Can you follow? Ito ang original position. And then, move natin yan 1, okay, move mo yan 90 degrees counterclockwise. Anong mangyayari kay 1? Mapupunta si 1 dito. Okay, si 2 mapupunta dito. So, ito siya. Yan yung R1. Okay? Next. Si R2 naman. So, dito, from here, we have to move again 90 degrees counterclockwise. So, what happens to 1? Si 1 magiging dito na. Okay? So, 1 is there already. And then, what happens to 4? 4 here. Okay? And 3. And 3 rather, 3 up. And so on. So, how about R3? R3, okay, from R2, 1 counterclockwise rotation by 90 degrees. So, what happens to the vertices? 4 will now be below. There. 3 will take the place of 4. There. Okay? 2 will take the place of 3. There. And 1 will take the place of 2. Okay. So, that's it. R3. Next. Ano yung XY, D1, D2? Okay. XY, D1, D2. Si X naman is a reflection with respect to the X-axis. first. X-axis. So let me copy this. What will you do? This is your x-axis, yes? So let's go back to the previous R sub O. What are we going to do with R sub O? Flip it over. Rotate it. Okay? Oh no, not rotate. Reflect it along the x-axis. So what happens to that? Anong mangyayari kapag i-reflect natin? Itong dalawa pupunta sa taas, okay? And these two will be brought down. Hope you could follow. So, if I reflect with respect to the x-axis, reflect this with respect to the x-axis, 3 and 4 will take the place of 2 and 1. So, let's see. Correct? Okay. 3 and 4 took the places of 2 and 1. Okay, so in your paper, if the original position is this, okay, the original position is this, flip it over or reflect it with respect to the x-axis, you'll have this. Ba? Okay? You'll have there 4, 3, 2, 1. 4, 3, 2, 1. How about y? Y, from your original position this time, reflect it, okay? Reflect it along the y-axis. Ito yung y-axis. So, this is the y-axis. Reflect it over the y-axis. So, you simply have to do it this way. What will it be? So, from the original position, from RO, if we reflect RO along the y-axis, then 1, 4 will take the place of 2, 3. Okay? 1, 4 will take the place of 2, 3. So, what will it be then? What will be the position of the vertices? So, tama. 1, 4 took the places of 2, 3. Next, how about D1? Diagonal 1. There are 2 diagonals. So, let me draw. There are 2 diagonals of the square. D1 and D2. Okay, so you have 2 diagonals of your square. D1, that which comes from your first quadrant to the third quadrant, that's D1. D1 from the first quadrant to the third quadrant, that's D1. And then D2, that which comes from the second quadrant to the fourth quadrant, that is D2. Okay, D2. Now, so D1, what happens to D1? So, from the original position, reflect the square with respect to the first diagonal. So, what happens? 2 and 4 will shuffle places. Yes? Okay, 2 and 4 will exchange places from the original position. Let's go back to the original position. Where is D1? D1. This is D1. From the first quadrant to the third quadrant, this is D1. What are we going to do for D1? What is D1 equal to? D1 is defined as the reflection with respect to the first diagonal. And when we mean first diagonal, it's the diagonal drawn from the first quadrant to the third quadrant. So what happens? Over 4 and 2 will exchange places. But 1 and 3 will remain. Tingnan natin. Sa baba si 2, sa taas si 4. Let's see. Okay. Baba. Ay, bakit hindi ko binaba? Parang mali. D1. D1, flip this over. Should be 2 here, 4 here. Or baligtad tayo. Second diagonal. This is the second diagonal. This is the second diagonal, 1, 3. Please check on our illustration. Nagkabaligtad. It's the opposite. It should be this. But it's okay if we stick to this PowerPoint. Or let me just draw an arrow. Okay, and this should be here. Okay, please take note of that. And then for D2, flip this over. The second diagonal. Flip it over like this. So, 1 and 3 will swap places. Ito. 1 and 3 will swap places. Can you follow? Yes, ma'am. Yes, ma'am. Kaya nyo pa? Or I leave it as an assignment so we could continue by next meeting. Can we continue next meeting with the set of symmetries of a square? No one is responding. Yes, ma'am daw. Okay. Mahaba-haba pa kasi ito because we will look into all the properties. 4 properties that we are going to check. Remember, for group, closure, associativity, existence of inverse, of identity, and existence of inverse. So, if we continue, I think I will eat up your time until 1 o'clock. So, it's up to you. I can continue. But if you wish, we could cut it short. And we will continue for next meeting. Shall we continue or may we have it for next meeting na lang? Okay then, so we end up with symmetries of a square. But since we did not finish it, we will continue with it next meeting. Okay, so please take note of your assignment. Thank you very much once again for actively participating even through chat only during our discussion today.